In section 7.1, we're going to look at simplifying radical expressions, but specifically in the first part in the video notes, we're going to be looking at the domain of some rational functions. All right. Before talking about domain, let's just take a look at what the graph of a rational function looks like, 1 over x, because we can often get a lot of domain information from seeing the picture. So we have a picture here already drawn out, and we're going to fill in the table for the y values, though we can already see that it has been sketched here. So if you plug in the x value, it's going to go into the denominator, so 1 over negative 2. Looks a little awkward. We're going to rewrite that as negative 1/2 as the ordered pair. We don't like to keep negatives in the denominator. It's more simplified to swing it up top. 1 over 1 is negative 1. 1 over 0. So when you have 1 over 0, you know you can't divide by 0, so you have to say that that value is undefined. 1 divided by 1 is 1, and then 1 divided by 2 is 1/2. Okay, so the interesting piece about these rational functions is going to be that value, in this case it was 0, that causes the fraction to become undefined. You can't plug 0 into the denominator, so you can't evaluate at that place. Now you also see that showing up in the graph right here as a vertical asymptote. The graph is broken into two separate pieces around that undefined value, around that 0 value. So the equation of the vertical asymptote is x equals 0 for this rational function. If your denominator is different than x, if it is a different polynomial function, whether it's linear or quadratic, you're going to have a different asymptote. But this is the basic asymptote from the first picture here. All right, so at the bottom of the page we have just some information about vertical asymptotes. So vertical asymptote is going to be a vertical line, and because it's a vertical line, that line will be x equals a number. Like this is a vertical line, x equals 0. X equals a number for a vertical line, which corresponds to the zeros of the denominator, places where the denominator is equal to 0. When the rational function is reduced to lowest terms, and that's going to be a key factor. If the rational function is not reduced to lowest terms, if those values are also not in the domain, they will not make asymptotes. So we always have to reduce first. Okay? Now, when you're graphing, if you're graphing a rational function by hand, make sure that you do not graph the asymptote as a solid line. Sometimes in older calculators, it kind of connected from one end to the other because it couldn't deal well with asymptotes. New calculators and online software is much better at that than they used to be, so often the asymptotes won't show up at all. But because a by hand graph has to absolutely make sure it doesn't go through the asymptote, we like to dot it in so we have a guideline to make sure our graph stays on either side of the asymptote. They're not part of the function though. If you want to graph them, you must use those dotted lines, like I dotted that red line in right there. All right. Now, rational expressions at the bottom here, aka algebraic fractions, like that 1 over x, can be in the form of any polynomial divided by any other. So p of x and q of x are polynomials. You have a polynomial in the numerator and a polynomial in the denominator. Now, specifically, the domain, which is what we're talking about here, of the rational functions is a set of all numbers except those that make the denominator 0. That make your denominator equal to 0. All right. So let's take a look on our next page and talk about some more domains. I'm going to find the domain of each function listed here. In this first one, it's 35 divided by 2x. I just want to remember when I'm talking about domain, we're talking about denominator. So I'm going to set the denominator equal to 0. So if 2x is equal to 0, I'm going to find first of all what that value is. Divide off our 2. X equals 0. Remember that the domain says that x is not allowed to be 0. So when you write your domain, we often use set notation, and you'll see why in a second for this. It's the set of all x such that x is not equal to 0. The shorthand for set notation is often in inequality notation. It's not an inequality this time, it's just an excluded value. So, and then we have our interval notation as well, our traditional interval notation. Interval notation would be, it's the interval from negative infinity to infinity, excluding 0. It's the interval from negative infinity up till 0, including the 0 to infinity interval. So that goes all the way from negative infinity to infinity with that break at 0 to stop 0 as the one excluded value. Okay. Now, if you're taking out one or more values, more than one values, the interval notation actually gets a lot longer than the set notation. So for these, it is traditional to use set notation. We're going to shy away because this is not an inequality. There's no official inequality notation for it, not being an inequality symbol. So we're going to sway into the formal set notation for these, using those squiggly brackets and everything. A lot of times in online software systems like my math lab, the squiggly brackets are already typed for you, and you have to type in the excluded value on the inside. But we're going to try to work on writing by hand that full set notation for the domain. Cool. Let's look at another one. All right, and we'll just, in the future, for the rest of these, just be working on that set notation. We don't want to write the interval in both of them for all of these. So, our domain, again, focus on the denominator. First, find out when it is 0 so you can throw that value away. So 3x plus 4 equals 0. Solve it for x, so we're going to subtract the 4 off. 3x equals negative 4, and again, you can pause your videos if I start writing too fast here. Divide by 3, divide by 3, and so that gives us x equals negative 4/3. X is not allowed to be negative 4/3. So that means that the domain is a set of all x such that x is not equal to negative 4/3. All right. So looking at the bottom half of this page, we've got two more functions. The difference between the top two and the bottom two is that the top two had linear denominators with no powers. These ones have binomial denominators. So we're going to factor when I set the denominator equal to 0. So I've got, first of all, my denominator to focus on here, my a squared minus 3a minus 10 equals 0. So this factors into a minus 5 and a plus 2. If that looks good, let's see, negative 5 and 2 add to negative 3 and multiply to negative 10. So a minus 5 equals 0. Set each factor equal to 0. A plus 2 equals 0. If I add the 5 to both sides, a equals 5. And if I subtract 2 from both sides, a equals negative 2. All right. So the domain is the set of all a such that a is not equal to, and usually we'll just put those not equal to values back in numerical order, so negative 2 and 5. All right. Now, if anyone noticed while we were factoring these, I didn't point it out yet, so you may not have noticed it, but noticed that if this was in the denominator, that this a minus 5 factor right here would have reduced with that a minus 5 factor up there. Sorry, I gotta watch my pages on my screen a little bit better there. Sorry if that bottom was off. Okay, so my domain cannot include 5, and it cannot include negative 2. But on the previous page, we talked about vertical asymptotes and domains. And the vertical asymptote only came from the reduced fraction. So these two pieces will reduce, when we get to reducing in a fraction, these two pieces will reduce, which means that a equals negative 2 is a vertical asymptote, and a equals 5 is not. If you want to know what it is, it's a hole in the graph. So the graph will have a little blip at a equals 5. Okay. If you want to think about what that would look like, I've got that function graph for us over here. I just use x instead of a. And we had a vertical asymptote at a equals negative 2. We can see that showing up here. But at 5, there is no asymptote. But what we can see is it's undefined. If I can pull my mouse down, you can see that the circle opens right there. So there's an open circle at that point, not like the regular dots, it would be anywhere else. The function is still undefined if that value is not in the domain. Open circle. Interesting. Okay, so I could draw a quick sketch of what I might do if I had to draw this by hand. We had that asymptote at, if I can remember what this looks like, and then I had an open circle at 5. And I think my graph looked like that. Oops, that as well. Okay, but the important parts were my asymptote happening at only one of those domain values. Okay. Now, I didn't mention that in the previous two because it wasn't an issue in parts A and B, because in parts A and B, I did not have a factor that reduced. So if we were interested in going back up there and filling in that information, we could fill in that x equals -4/3 is a VA, short for vertical asymptote, and x equals 0 is a VA, short for vertical asymptote, because those were not values that reduced in the numerator. All right. So it's looking at our last one right here, find out what happens. I'm going to look for a domain. Again, I'm trying to extend a little bit here on that asymptote piece just for some more information because the previous page was talking about it. We'll talk more about asymptotes when we get to our class. First, let's begin finding the domain. And so I need to get the denominator here factored. So 2t squared plus 8t minus 42 equals 0. Those all have 2 as a GCF. Factor that out. T squared plus 4t minus 21 equals 0. And you think of a number, pair of numbers that goes into 21. 7 and 3. If I have a positive 7 minus 3, that's going to work. It's going to give me a 4, and then multiply to a -21. So we've got 2t plus 7, t minus 3 equals 0. Set each factor that contains a variable equal to 0. The 2 doesn't have a variable, so that isn't going to be part of it. Just the 2 factors that have variables. Okay, subtract 7, add 3. So t equals -7, t equals 3. And our domain. Remember that these values are excluded because the denominator is not allowed to be 0. So it's a set of all x such that x is not equal to -7 or 3. I notice that the numerator is already in factored form, t minus 8. If it's not factored and you want to look at vertical asymptotes, you would get your numerator factored. And that doesn't reduce with our factored form. So, just for fun, we can make a note that both of those are vertical asymptotes. This function has x equals -7 and x equals 3 are both VAs for vertical asymptotes.